All right, we are now recording. Let's get the slideshow set up from this slide. Okay, before we get going today, and I'm going to turn on this projector. You have to hold it down longer than most. Let's just go over quickly what we've done and what we still have to be done. And I probably want this to be said on here too, so let me get close enough to make sure this is recorded. We're moving along in the term pretty well. I mean, we're more than halfway through the mini-term, right? Okay. We've had 1, 2, 3, 4 weeks of the 8-week. This is we're past midterm for the mini-term. So, and then part of the last week is going to be your finals. So we really don't have super lot of time to go. And this class has been pretty good in having 1, 2, 3, 4, 5 people have already turned in the papers. That's pretty good. That means there's more than 5 that haven't turned in the paper. So please don't forget, you got the paper. Don't put it off till the end of the term. Too much is happening then. All right. Also wanted to remind you this. The first lab, I have 2 people who haven't turned that in. The first test happens to be the same 2 people who haven't done the first test. Lab 2, 2 people haven't done that, not the same 2. The second test, 2 people haven't done that. The third lab is your moon lab, which I hope you're doing, and get that done whenever you can get it in. That'll be great. Test 3, 1 person hasn't turned that in. Lab 4 was our trip to the planetarium. So if you're there, you got your 25. If you weren't there, you didn't get your 25. But that's an optional lab, so do that. Lab 5 then was the one from last chapter. That was the minerals lab. That was a computer lab. I've got 1, 2, 3 people haven't turned that one in. Test 4 is the one we took last time. I have 1, 2, 3, 4, 5. 5 people haven't taken that. Okay? So, I'd love to be returning some of these paper, folks. I'm carrying around a whole stack, but I can't return them until you get your things in. So please catch up your old labs and your old tests so we can do that. Now, that was the commercial message. Let's get on. Yeah. Oh, you're distracted. Yes. There's not a place?
It's under tools. You put tools and you'll see my grade.
See, I don't see the student side of it. You got it?
I have a question.
Yeah.
Are we having a mini-term test? Or
No. I mean, all these are in the middle test. So there's not a midterm test, but there's a final at the end.
All right.
Right. All right. Good question, though. Now, we're in chapter 18, and we don't have much more to do in 18. So we're going to finish 18 today, and we'll start 19. And then when 3 o'clock arrives, we'll do the lab for chapter 18. Now, the lab for 18 is a little different from the other labs in that it's not, there is a lab part, but it's a very short lab part. Basically only 10 points worth, okay? And which also reminds me, she didn't have a copy this morning. I left it there last night for her to copy, and I meant to go by today, and I didn't. At the break between class and lab, I'll go get the labs. Okay. So the last 15 points on the lab, and we'll talk about this when lab gets here, but you'll be answering questions from the book. Okay? So that's your last 15 points on the lab, but we'll talk about that later. So we'll go on. That means that then next time on Thursday, we'll continue in 19. We may actually finish it. We'll see how far we get today. And if we do finish it in time for the lab, we'll have the lab, but then we'll have the test on chapter 18. So I know the test will happen in 18. I know the lab for 18 will be today. Just depends on how far we get in 19 today and next time, whether we'll have the lab then or not. Okay? Any questions? All right. We were talking last time, and I'll go and turn off this if y'all can see well enough. It seems like it's darker up here than what I remember it to be. Okay. Last time we were talking about the movement of plates. This is plate tectonics, is the name of the chapter, and the movement of plates. There were 3 types of movement. Does anyone remember those 3 types of movement?
Convergent,
Convergence,
divergent,
divergence, okay. It will be, say again? Transform boundaries, okay? That's very good. Now, let's see, we started with divergence. And what was the prime example of a diverging plate, the result of this?
I moves away.
Trench.
What?
Trenches.
I can't hear. My hearing's so bad.
The trenches.
Yeah, okay. Now the trenches are more from converging, and we'll talk about that later. It's the ridges, because when the plates separate, lava comes up, magma comes up from below and forms a ridge there. Whereas the main ridge, the one that we talked the most about, which ocean is getting wider? And the mid-Atlantic ridge, exactly. Goes right down, whatever the center of Atlantic Ocean is, it follows that same pattern around Brazil and all the other things. And sure enough, and we looked at several things about that. Then we moved to converging plates, okay? And the first converging plates we talked about, in fact, this may be the first one. Let me go back one slide. No, we talked about ocean-continent plate convergence, and that's where the trenches come from, or some of the trenches. And now we're looking at ocean converging, converging plates. And Brianna's here. All right. We're still missing Darius, Bianca, James, Carrie, and Terry.
I don't think James is coming.
You don't think James is coming? Okay. Okay. So we're starting today with ocean plate convergence. Now, remind me, what happens with ocean continent plate convergence? What is the deal with that? What always goes where? The what? The ocean continental plate convergence.
The ocean plate goes under the...
Absolutely. The ocean plate, and the word for it is subducts, or goes under the continental plate. What's a major reason for that happening? What's the ocean plate, typically the material of the ocean plate?
The mantle.
Basaltic rock. And what can you tell me about basaltic rock? This is last chapter, but it all ties together.
Igneous rock?
Yes, it's an igneous rock. What are the components of it? Or one of the components. Okay. Tell me something maybe about its color. Dark. What does that indicate? High.
High temperature.
Say again?
High temperature.
Not by the time it's in the bottom of the ocean. It's about, no, but it came from igneous rock, so at one time it was high temperature. But the dark color typically indicates high iron content. And high iron content means it's, okay, how about the continental plates? What are their primary ingredient? It's also an igneous rock, by the way. What's the major? Say again? It is a silicate, okay? And so is the salt, is a silicate. It's an iron ferromagnesium silicate. But the rock rather than the minerals, the rock that the continental plates, okay, it has oxygen in it. The say again?
Sedimentary.
No, it's an igneous rock, not sedimentary. Now, there are plenty of sedimentary rocks in the continental plates. Yeah, that's true. But primarily, the igneous rock that makes up the continental plates are the granites, exactly. And what can you tell me about granites? Especially color-wise, compared to basaltic. Lighter color, which indicates what? Less iron. There's a little bit. You know, you get a little bit of peppery spackling in your granites. That's because there's some iron in there, but not nearly as much as you have in the basalts. So, those facts, basalts are high iron content, granites low iron content. What does that tell you? The granites are more or less dense. Which? Less dense than the basalts, so therefore the basalts tend to subduct under the granites. So the oceanic plates go underneath the continental plates. And that's where that trench is. The continental trench is right off the shore of where that's happened. But what's happening with ocean plate convergence? All the ocean plates are basically basaltic. What gives here? Okay? We don't know why, but one has to subduct under the other. Okay? I don't know. They got there first. I don't know why one subducts under the other. Maybe that's just not as dense of basaltic rock. I don't think they know. But it does happen. So when this does happen, you form a trench there too. And perhaps an underwater ridge as well, because when the one oceanic plate subducts under the other, the trench is over here, but the ridge is right on next to it. What else is happening when one goes under the other?
Friction.
Friction, enormous friction. And friction causes?
Heat.
Heat, and heat does what to the rock? Melts it. And then you tend to have what happening? Volcanic activity, exactly. So there's all sorts of mess. That's why they're associated with deep-seated volcanoes, because that usually happens way underneath, and the friction is so great under there, there's a lot of pressure, and you're also getting closer and closer to the core. That's hot itself, so things are heating up, and you associate with these deep-seated volcanoes. Now, where this is happening, the two plates are converging, one's going under the other, subducting under the other, and you have this volcanic activity that creates these arcs of islands, okay? The islands are mostly volcanic islands, okay? They form where the melted subductive material rises up above sea level through the overriding plate, okay? That's the description. Here is the picture of it. Okay, now again, these are both oceanic plates. And originally these volcanoes weren't here. They were underwater. But like I said, either one plate tends to be a little above the other, or maybe it's a thicker plate and the thinner one goes under. We don't know why. It started a long time ago, but it happened. And so where the one plate goes under the other plate, that's where the trench occurs. But back here, where all the friction of this plate having to move, you know, if on one side of the globe the plates are spreading, the globe isn't getting any bigger, so then you have subduction over here on the other side, and here you get lots of, already it's hot down here, it's near the core, already hot, and then you have the additional friction here, you start melting more material, they find cracks, because guess what? One plate going under another plate, probably it's going to cause some issues, okay? Or fissures, okay? And when that happens, there could be breaks in the upper plate, and then the magma makes its way to the top, and then you have a volcanic vent. And some of these are below water, that's your ridge. When they're above water, that's your island arc, or your arc island. Does that make sense? Okay. Okay. Now, before we get to continent, sorry about this. I'm going to pause Screencast-O-Matic just for a moment. Here. I'll turn on the lights again. Now, you expect to find many island arcs in the Atlantic? Not really. That's a diverging plate area. You do get places like Iceland, which the volcanic activity has come to the surface there, and maybe some other places up here, but you don't typically have lots of arc islands in the Atlantic. There may be a few, just where weaknesses or something in the plate. But in the Pacific, that's where the plates are coming together. Spreading in the Atlantic, coming together in the Pacific, boy, do you have arc islands. One really famous, at the end of Alaska, is the Aleutian chain. Look at that arc. That's where the Eurasian plate bumps into the Pacific plate. And there you have arc islands. Okay? Actually, the whole nation of Japan, arc islands. Okay? The Eurasian plate, again, hitting into the Pacific plate. Okay? The Philippines. Remember, there's that little plate called the Philippine plate, where it hits the Pacific plate. The Philippines are a big group of arc islands there. Look at Indonesia. Look at that. It's shaped just like an arc island, where the Pacific plate bumps into the Indian Australia plate. Look at it. They're just all over the place. New Zealand, arc islands. And just about all these. Melanesia, Micronesia, Kiribati. Okay, I don't even know several of these. Somewhere is the Marianas chain, okay? The Caroline Islands. Now, some of these are out in the middle of the Pacific. That's not two plates. It's just where the plate's under a lot of pressure and maybe the weak place, and that's where it comes up. The Hawaiian Islands are an island arc chain, okay? I've got to find it. Right there they are. And actually that goes all the way up to Midway, Wake. I can't see Wake now, but it's somewhere in there. But there's a whole island chain there. They're just all over in the Pacific, these arc island chains. Now, no one else came in while I stepped out, did they? Okay, so I just wanted you to see examples of that. All right. So we have ocean plate converging with continental plates. Okay. We have ocean plates converging with ocean plates. What's left? Continent plate. A good read. Okay. Continent plate convergence. Now what materials do we have? Continents are made of, the continental plate, granite. This is granite, this is granite. And they're thick. Remember, they're thicker plates. The basaltic plates tend to be thin, but dense. The continental plates tend to be thick. I don't think you're going to have a lot of subduction going on there. So what happens?
They both go up.
Boom, yeah, they go up. Exactly, they go up. The less dense granite-type materials resist subduction. Neither one wants to go underneath. So the colliding plates, you read the well, doesn't it? Piles up, okay? Producing a deformed and thicker crust, but made out of these lighter materials, okay? Lights again. Okay. Now, if I said, name me a major mountain range, what comes to mind?
Himalayan.
Himalayas, good choice, okay? Himalayas are where? Why did he choose Himalayas?
Yeah, it's on
Oh, they're on the board. He's reading again, isn't he? Okay. All right, I'll forget. I got to stand in this way. All right. The Himalayas are north of India. Basically, Nepal, Tibet, part of India, part of China. What's happening there? Eurasian plate, continental plate, The Indian-Australian plate at this point is continental. Crash. Now, it's not a big crash. It's a slow crash. They're going into each other. Something's got to give. Guess what? The Himalayas are what's giving. They're growing. Okay? What is the most famous mountain in the Himalayan range?
Everest.
Everest. What's special about Everest? Say again? Tallest mountain in the world. And growing. Okay? Because these plates are still converging. And guess what? You hear about earthquakes in this region, in China, remember fairly recently, at this edge of the Himalayas, they've had some pretty major quakes now because it's still being forced upward. But you don't have to go to the Himalayas now. By the way, remember on our coast, South America, that's from the Pacific plate subducting. This is oceanic continental plate subducting under the South American plate. That's why the Andes grew where they are and still growing, because that's subducting there. In North America, part of the Rockies, and they're still growing too, but they're well inland. Okay? Well, that's because the force from here is still pushing that way as well. But the ranges right along the coast, like the Sierra Nevadas down here, the Cascades up here, and in Alaska, there's some pretty tall mountains too. In fact, before Alaska was added to the U.S., the tallest mountain in the U.S. was Mount, let's see if I can find it on here. I know it's here, or I think it's on the map, I don't see it. But yeah, there it is, Mount Whitney, the tallest of the mountains in the contiguous 48 states. When Alaska was added, Mount McKinley was taller than Mount Whitney, so it became the tallest. And that's inland quite a ways, but still from plate convergence, okay? Pushing up. But that's mostly ocean continental conversion. Continent conversion, the Himalayas are your best example there. And still growing, okay? The Tibetan Plateau is a bit further inland, and the Himalayan mountains on the edge of that. And not only is Everest the tallest mountain in the world, but I think number 2, 3, 4, and 5 are also in the Himalayas. I mean, that's a tall range of mountains because of that continental convergence. Make sense? Okay, so here we have it. One continental lithosphere. Now, what is lithosphere? It was on there before I meant to ask. What makes up the lithosphere? The crust?
And the upper man.
Upper part of the mantle. What's beneath the lithosphere? It's another sphere, but it's an asphere. Say again? A asthenosphere. A asthenosphere is that sort of semi-liquid, semi-plastic layer that the plates float on. So here you have continental lithosphere, the continental crust, but also the upper part of the mantle. On top of the asthenosphere, and when these are coming together, they have nowhere to go but up. And that's where they go. All right, does that make sense? All right. What two boundaries have we talked about so far?
Convergent.
Diverging boundaries, converging. 3 types of converging boundaries.
Transform.
Second,
Say that again.
3 types of converging boundaries. Oceanic continental, ocean, continent. Okay, but not incontinent. Okay. Now, the third type of boundary is your transform boundary. What's going on there? They're not diverging. They're not converging. What are they doing? Going past each other. They're also sometimes called shear boundaries because they're moving past each other. Occurs when 2 plates, I thought you would get this one, slide by each other. Not converging on each other, not diverging, but slide by each other. Guess what? They don't slide very well, do they? They're rough, they're jagged. Those plates are not nice even well lubricated areas, they are rough, okay? The crust is neither created nor destroyed. Where is crust created? What kind of boundary?
Converging?
Diverging, because that's where you get magma coming up. And where is crust destroyed? Converging, because it either subducts down and melts or crashes together and grows taller. So you're that's sort of like a creation, but it's not. It's actually some of it is destroyed. So mostly the ocean subduction, that's where it's destroyed. Okay? But here in the transform boundaries, neither created nor destroyed. Irregularities in the movement, however, happen. They are trying to slide past each other, but they're not particularly slick. Okay? So they're jagged, they're awkward. They get stuck on rocks poking out into the other or something like this. So what happens? Yes, a brace will break off, and what happens then? Earthquake, exactly. That's what causes earthquake. The sudden jerks are not guys, okay, not in Washington, no, never mind, okay. These are the sudden changes as they're trying to slip, but they get hung up, and then when they let go, that produces an earthquake. And the most famous here in the U.S. is the San Andreas Fault along the California coastline. I'll turn on the, well, do we have a slide here? Not quite, okay? So I think there's figures in the book. Okay. The San Andreas Fault goes up the west coast of the U.S., and why did we build cities here? Los Angeles sits almost on top of it. San Francisco, several major quakes in San Francisco. Back at the turn of the 20th century, the 1800s and 1900s, major earthquake in San Francisco. Okay? We'll talk about this more in a couple of chapters. Okay? Or is it later in this chapter? I think, no, it's in a couple of chapters. Okay? So I won't go do too much on it. But guess what? And this was actually in the news this morning. I don't remember. Yeah, I remember what it was about. Here's the Baja Peninsula, which is in Mexico, but this body of water up here is the Gulf of California. Okay? That basically, at least in my understanding, is about the San Andreas Fault. It just happens to be underwater at the time, and it comes on up and curves around, and somewhere here it probably goes out to sea. But for many of the areas there, it is actually just a little ways inland, and that's where the two crusts are sliding past each other. And that's where the earthquakes happen. Now, in my lifetime, I wasn't alive back in 1900, not quite yet, but during my lifetime, there has been a fairly major quake in San Francisco. Anyone remember what that one's nickname was? It was the World Series quake. Oakland was playing San Francisco for the World Series, and that's when the earthquake happened while I think a game was underway. It was pretty amazing. Now, remember, San Francisco sits on a peninsula. I already turned off the light. But inside that peninsula is the San Francisco Bay. Golden Gate Bridge goes across the peninsula to the northern part. Beautiful bridge there. I've been under it several times on a ship because we were stationed inside there for the when I was in the Navy. So going and coming, we went under it many a time. But then there's also some pretty other major, like connecting Oakland to San Francisco. So there was the Bay Bridge Tunnel. Now the tunnel part was because there's an island in the middle called Yerba Buena Island, and they tunneled through the Yerba Buena Island and then had the bridge on either side of that, you know. And the Bay Bridge, and basically what they did, one lane was underneath the other lane. So I can't remember, eastbound went one way, one the other. And when the earthquake happened, the top part of the bridge landed on the bottom part of the bridge. You didn't want to be in a car going that way, okay, because there were many cars trapped and probably many people killed, at that time. And it seems like just a few years after that, another major quake down in Los Angeles, and you had a lot of expressways again, bridges, overpasses collapsing down on cars going underneath. So some pretty major quakes along the San Andreas Fault. Okay, along the coastline, not right on the coastline, inland a little ways. Now, in a couple chapters, when we talk about building the Earth's surface, we will actually see some amazing pictures of things along the San Andreas Fault. But we'll just hold off on that until we get there. Now, what is causing all this? Now, let's see. Before we get too far, let me mention a few things in the text, well worth your attention. A closer look on the top of page 468, measuring plate movement. They have actually and do actually measure this. So that's a really nice little blurb to read. I would highly recommend it. There's a few examples here, and they're talking about, and we're not going to do these because some of them involve math that you would have had in the earlier sections that we didn't do, chapters we didn't do, but talking about the earthquake, how far some of these major quakes are from some of the trenches. And they're fairly close because the trenches are here and the quakes come further down, just like the earlier picture showed. Like here. Your trenches occur here, and then your volcanic activity and also earthquakes can be over here. See, in addition to volcanic activity, when these plates which are being subducted hits the snag down here and then gives way, you have earthquakes there as well. In fact, I'm guessing that's the one that caused the big tsunami in Fukushima in Japan. That was a Pacific plate subducting under the Eurasian plate, and sure enough, that made it. And then, this is another sort of mistakes and misunderstanding. Bye-bye, California. Okay, is it true that California, the San Andreas Fault, going to break off and California is going to fall into the sea? No, that's not what's happening. Earthquakes are not the opening of the earth and people falling in. That's in movies. That's Hollywood. Okay, it's not real life. Okay, earthquakes are vibrations, shattering. Very seldom do you have any separation at the surface. At the bottom of the mid-Atlantic ridge, yeah, you have separation there, but we don't see that. That's the diverging boundaries there. So, nice little blurb there, well worth a read there. Bye-bye, California. Mistakes, misunderstanding. Okay. So what are our understandings? The present day understanding of what's going on. Some big questions we do not know the answers. Why are the plates moving anyway? What's the causative factor here? You would think they'd say, hey, it's a lot easier to just sit still. Okay, why are they moving? Okay, what drives the plates? And actually, there's probably several working hypotheses now. Here is one. The current working hypothesis, they say it's due to or because of these convective cells in the asthenosphere. Now, what do we mean by convection? Anyone have an idea? Okay. You probably are right, I just can't hear. Okay, certainly the asthenosphere is where a lot of that magma is coming from, and it is down there, okay? But what do we mean by convective cells there? Do you remember the old cookware that you could see through? They call it visionware. It was sort of a glass-looking pots and pans that you could actually see through. It was usually colored amber or something like that, but you actually saw it. Anyone know what I'm talking about? You never have. Okay, you've seen it. You could look at it and watch the water boil, couldn't you? Okay? And what you notice then, when you're looking at that, you can look in another pot and sort of see it. You can see it from the side here. The hottest part of the eye would be probably right under the center. And then to the pot, because it's exposed to the air on the outside, that's the cooler part there. And convection is illustrated when you saw the water rising in the middle of the pot, because that's where the greatest heat was, and coming to the surface, and then you could see these eddy currents doing like this. That's convection. The hottest magma or whatever coming up and cooling off and pulling down. So that's what they talk about. The hot fluid materials rise at the diverging boundaries, and then that doesn't come through the diverging boundaries moves along the outside, actually sort of dragging the plates apart. Okay? So the hot fluid materials rise at the diverging boundaries because of this convection that's going on. Some escapes to form new crust. The remainder spread beneath the lithosphere in the asthenosphere, dragging the overlying plates with it, pulling them apart. If it's pulling them apart, there's nowhere to go, so then you have convergence on the opposite side. Okay? Sounds like a good theory. Problem? How do you measure that? How do you test this? Okay? Theories are great, but you've got to be able to test them. There's very little supporting evidence. It's just a good idea. We just don't know if it's right or not. Okay? Now, these illustrations here kind of show what they think is going on. This must be the Atlantic. Here's the mid-Atlantic ridge going up here. They call it a rift valley. That's where it sort of sinks down when it cools. But the ridge that forms on either side. You got earthquakes going on here. Here's the convection. The hot mantle rock is coming up, making its way to the surface. Some escapes, and some drags the plates apart. Okay? So that's one idea. The ocean crust is over here. It goes underneath the continental crust. We know that. There's your oceanic trench right there. That's caused by the subduction of the oceanic crust under the continental crust. Continental crust, thicker but lighter material, gets raised up, and somewhere down here you have problems. As that moves, it gets snagged at other things, and you can have little or big earthquakes, deep earthquakes here. But somewhere down here, it gets hot enough that you actually form magma. And the magma then, if it finds cracks or crevices, especially because these plates have been crushing into each other, coming to the surface, then you have your volcanoes. And that's why all around the Pacific they call it the Ring of Fire, because that's where you have your earthquakes, that's where you have your volcanic activity. You also have oceanic plates going underneath other oceanic plates, like this, and maybe this is why the movement happens, because it came from here, so this one's moving, that one's stationary, so this one had to go under, and then again you have friction, earthquakes, volcanic activity, all that going on. You have another oceanic trench here. The most famous of those trenches between ocean plates, does anyone know the name of the deepest part of the ocean? I actually mentioned the name of the islands earlier. Yes. Okay, Marianas. The Marianas Trench. Let me find it. Guam is in the Marianas. I just have to find. There they are. The Northern Marianas Islands, Mariana Islands. And here, somewhere down here, are the southern ones. But here is one of those island chains. Arc Island chains that you have here. And the Marianas Trench, I believe it's the outside edge of that, the eastern edge of that, is where you have the deepest part of the ocean, the Marianas Trench. And actually, in the last few years, I would say in the last 5 years, the Navy, I believe it was, or somebody, came up with a vessel, a submarine, that was very well protected and pressurized, that they could go deep enough to go into the Marianas Trench. And guess who they invited to go down for that? One of the early dives. It may not have been the first one. Who was the guy who did the Star Wars?
George Lucas?
I think it was him. I believe it was George Lucas. Got to go down in that and see where no man had gone before. You couldn't see much of anything. It's so dark, but they had lights. It said just what you saw, the types of fish and the life that was down there. Kind of eerie, weird, okay? But anyway, the Marianas Trench, deepest part of the ocean. We'll talk about that again when we get to the last chapter, which is the ocean, the Earth's waters. So we'll get there. Now, this may be the last slide. Let me see. Yes, it is. Here's a couple of other theories, and these sort of go together. Some say what may be the pull of this plate going down is what creates that, rather than the convective cells pushing this way. It could be the plates are pulling this way, and that's what's creating the rift. But who came first, the chicken or the egg? We don't know. It's probably a combination of both of those. One is called the magma push or something like that. The other is called the plate pull, the pulling down. And it's probably a combination of the two. We just don't know. But here's an example of that convective. I was pointing down here, but here it really is. The hot magma, if it finds a way, it goes to the top. If it cools when it gets here, it moves this way and does that. This motion here is what drags the plate. That's what the current hypothesis is. But also, when it's pushing the plate this way, then this part starts pulling on it because its gravity is pulling it down. So, probably a combination of the two. Okay. Does that make sense? Mm-hmm. All right, that finishes chapter 19. And again, all that I say, all that the slides say, are only reinforced by reading the book. So please read the book. There's a couple of more blurbs in the book that are well worth your read. One of these is a case study, GPS and plate movement. Earlier there was a thing on measuring plate movement. GPS has now enabled us because now your GPS that you have in your phone, in your car, wherever you have it and use it, it's pretty good, but it can be off by a few meters or more. The ones the military use, they can almost locate within a few feet of something. We don't get the deluxe model, we get the using model. So GPS has been able to document plate movement. So it's well worth a read there, the case study. New earthquakes and volcanoes, well worth a read there. In fact, it would be sort of fun to go back and see some of the more recent some of the more recent earthquakes, but also some of the more recent volcanoes. Many times these are previously thought to be extinct volcanoes that then reactivate. There's always something going on well underneath. There is a people behind the science. They have at least one of these in every chapter. They mention here Harry Hammond Hess. How's that for a alliterative name? Okay. U.S. geologist who happened also to be a naval officer. Okay. And I think it was around, it was during World War II, while he was in the Navy, he continued research while he was there. And he's contributed a whole lot to our understanding of plate tectonics. Okay? Then there's another, Science and Society, really good blurb here, geothermal energy. And it talks about some of the places. I don't know if they mention Iceland, but they certainly use it big time. There is also a place, the Juan de Fuca plate up off our northwestern shore there. But one use of geothermal energy is to generate electricity There are power plants in California, 10 sites. Hawaii, certainly they have them. Nevada, 10 sites. Oregon and Utah, 2 sites that have generated an awful lot of energy. And guess what, folks? That's clean energy. You don't have to build a dam. You don't have to you do have to help Mother Nature along, maybe get the water past the hot rock and stuff, but Mother Nature does most of the heating of the water for you. All you have to do is harness it. Well worth a read. And finally, the summary. Now, the summary cannot replace reading the chapter. Nothing replaces reading the chapter. If you haven't read it already, go back and read it before Thursday, because that's when we're going to have the test. The summary, I think, is one of the shorter ones of all the chapters we've had. The key terms is one of the shorter lists that we've had. Now, these are listed alphabetically, but they give the page number where they're first introduced, defined, or described. But then the biggie, I think, is applying the concepts. 52 questions on this chapter, which is, I think, a little longer than most chapters. Multiple choice with the answers given. I think that would be an excellent study tool for the test. Questions for thought, 16, that's about average. Okay? For further analysis, 4, that might be just a tad below average. But guess what, team? When I said you're going to have to answer some questions, that didn't include these multiple choice. Why? The answers are given. That wouldn't be very much fun, would it? It's these questions for thought and for further analysis. 16 questions for thought, 4 for further analysis. That's a total of 20 questions. You need 15 more points for your lab. I'll talk about it later. You can get it from these 20 questions. Do any 15 or more of these questions, and I would suggest you do this before Thursday, because this is going to be helping you study for the test. Okay? You don't have to do it before Thursday. You got a week to work on the lab, but if you do these questions before Thursday, that's going to be a great study guide. Okay? And then there's parallel exercises. If you wanted to do some of those, you could. Of course, those of you with the big books, you can't do Group A because those answers are in the back. So if you do any of the parallel exercises, you need to do Group B. Those are a little more involved, but you're certainly able to use those if you'd like. All right, any questions on Chapter 18? Any questions on testing? It'll be next time, the last 30 minutes, we'll have a test on Chapter 18. If we get far enough on 19 today and Thursday, we may have the lab on 19 before your test on 18. But we'll see how that pans out. All right. It's about 1:30, a little past 1:30. So we've got another hour and a half of class. Yeah, hour and a half of class. So we'll get some decent material covered in 19. Any questions before we start it? Okay. Do tell me that I did turn on the Screencast-O-Matic after I came back.
I'm pretty sure you did.
Okay, I thought so. Okay. It just was off, and I must have just accidentally hit it or something. Okay, let's get out of here and go to Chapter 19. And Chapter 19, not only following in the book, Chapter 18, but thematically it follows very closely too, if I can get it to open. Whether it opens or not, it still follows 18. Here we go. Takes a while. No questions so far. All right, finally it's here. Get the slideshow set up. And this chapter is building the Earth's surface. And the picture in my book is a little different from this one, but it's the same type concept. What is that? An active volcano, exactly, in the process of spewing forth. And what's that called? It's coming out of?
Magma.
That's lava on the surface, and it was magma underneath. Okay, liquid rock, molten rock, melted rock, magma underneath, lava on the surface. And you can see all this was previous lava. Not too long ago either. Very little vegetation has grown. My guess, this is probably one of the volcanic chains on one of the islands in Hawaii. I'm not sure, but that would be my guess. The ship I was on in the Navy, the first ship that I was stationed at full-time after I got my commission, was the USS Kilauea. I don't know if any of you have ever heard of Kilauea, have you? And by the way, I don't think it was accident. It's sort of sick sense of humor. They name ammunition ships after active volcanoes, or after volcanoes anyway. So if we ever do have a fire, it's a pretty major one, okay? We leave a big hole in the water, okay? So it hasn't happened recently anyway. Actually, it did happen in World War II. Our home port was named to be Concord, California. In the old days, it was Port Chicago, which was the port on the Sacramento River near Concord. But in World War II, they were in the process of loading a merchant ship with ammunition to haul over to the Pacific to fight in the war against Japan. And no one knows what happened, but anyway, there was a fire and an explosion, and Port Chicago is no more, okay? It blew up everything, okay? They rebuilt a pier there, but they didn't rebuild the town. So you drove, literally, it seemed like for miles over just flat area to get out to the where we were burnt on the river. Just decided it wasn't worth it building a town back there again. But we were named after Kilauea, the most active volcano in the world. It's been spewing. It doesn't have violent eruptions. It just spews lava just about all the time. So I'm almost guessing that's Kilauea. I don't know for sure, but it could easily be. The one that's in your text, or in my text anyway, it doesn't give a name for that one either. It could be Kilauea, or it could be one of the others. There was also the Haleakala, the Mauna Kea, the Shasta, the Mount Hood, the Vesuvius. And they used to, in the older days, have names like Pyro and Nitro. Also, they named ammunition ships after that as well. But nowadays, it's mostly volcanoes. Okay, core concept here, which is also on that same page. And the core concept here is building Earth's surface. It's not just volcanic activity, but the surface of the Earth is involved in plate tectonic processes, chapter 18, that result in the ongoing buildup of the surfaces. Now, we talked about one kind in the first slide we had, second slide we had today, the convergence of continental and continental thing, building up the Earth's surface layer is actually going up. Volcanic activity usually builds it up, not always. One active volcano, it wasn't active, but happened during my lifetime. It may have been before y'all were born. Anyone remember Mount St. Helens? Okay. When it blew up, it blew such a fierce, it had been an extinct volcano, they thought, for the longest time, like centuries probably. But when it blew, it literally blew the top off the mountain. So when it finished, it was actually shorter than it was to begin with because it lost the whole rock at the top. Okay? This is a picture, I think, of Shasta. I'm not sure. I believe that's going to come up later, which is also a volcano. You can just barely see an extinct, so far, volcano. I think there's another one right here. Okay? They haven't erupted in, again, centuries. Doesn't mean they won't, but they haven't. And you can see this is lava flow, okay, from when they did erupt, whenever that was in the past. But the surface of the Earth is involved in these processes that result in ongoing buildup of the surface. The next chapter, looking ahead, 20, is going to be wearing down of the surface, the erosive processes and things like this. We'll get there later. This chapter, building up. So, what we want to do first is interpret the Earth's surface. And here is the key principle for this and subsequent chapters, the present is the key to the past. This is called the principle of uniformity. There's other ways to express that. It's almost like what comes around goes around, almost, not quite, but sort of like that. Everything that's happening now has happened before, okay? There was probably a few generations ago the theory that everything that we now understand, excuse me, I think someone's looking for me. Oh, okay. Oh, okay, you're welcome to. You can go sit down if you like. Okay. All right. The principle is, the thoughts were way back then, there must have been some major cataclysmic activity that went on that formed the earth as we know it, and then it quit. And there's just been little things since then. Now we think that's probably not a good theory, okay? We think it's more properly the principle of uniformity, that what's happening now was happening before, and it's going to happen again. Rocks are changed today by the same processes that changed them in the past. We saw some of those rocks that were, especially the metamorphic rocks that had been changed under pressure. They've made it to the surface. The other rocks that are way underneath, they're being changed right now. Later we'll see them. Maybe we won't, but someone will see them when they come. The rocks changed today by the same processes that changed them in the past. Replace this catastrophic model of the previous thinkers, that's a few generations ago. The catastrophic events certainly contribute. When you have volcanoes, that's a pretty catastrophic event, at least for that area where it occurred. Like I mentioned Vesuvius. What's the story on that? Anyone know? Yes, there was a town called Pompeii at the base of the mountain Vesuvius. Now it's fixed in stone. Okay, they have unearthed and done archaeological digs there, and have found a lot about what life was like there. But basically, that was a catastrophe. They didn't have time to get out, to get away. Basically, everything got destroyed in place. Yeah, those contribute big time, but they've always happened. They will continue to happen. Now, the good news is we have ways to at least predict things a little bit better than they did in the past. We're still really bad at predicting earthquakes. They happen whenever they want. However, there are some things they measure, and they can say, look, it looks like there's at least a chance we could have something happen in the next decade or two. You know, that's not very precise, but at least they have a little bit better handle on it maybe than in the past. Okay, volcanoes, earthquakes. Now, meteorite impacts, they can detect them further away, okay? They can see when there is something coming and whether it has a chance of interacting with us or not, if it's big enough. Now, the smaller ones, quite often we miss those. But a lot of science fiction has been written about the big one that we just didn't catch in time, and here it comes, and what's going to happen then. But yeah, those things have occurred, and they will continue to occur. But it isn't what forms us. The things that form us have been things that have always been happening and will continue to be happening. A follow-up on that is this concept of diastrophism. Boy, they like big words in this chapter, don't they? The process of deformation that changes the Earth's surface. Diastrophism, okay? That sort of reminds me of the word diaspora. Have y'all heard that concept? It's like the Jews after World War II were spread, but back in their history, you know, they were spread by the Romans and many others before. The diaspora of the Irish, you know, when they had the potato famine, you know, when people, and what's happening in Syria is a diaspora, you know, a spreading, the process of change. So diaspora, I think that same prefix, a big change is happening. Trophism is something to do with the buildup of things, so the process of deformation that changes the Earth's surface. produces structures such as plateaus. We mentioned in the last chapter right at the end, the Tibetan Plateau, okay? That's Tibet, which is raised area, still pretty flat, but it's been raised up because of that continental collision. It's not the word we use for it. Goodness, why is my mind going blank? Convergence. That raised the Himalayas, also basically raised the whole plateau of Tibet. Okay, so those plateaus have been formed. The mountains, and mountains are usually caused by one of three ways, and we'll talk about all three of those later in this chapter. One of these is volcanism. That's volcanic. Okay, movement of magma. Okay. Diastrophism is related to volcanism and to earthquakes. And those go hand in glove, right? When you have plates moving past each other, you have earthquakes happening when they give way, and when the friction causes heat and melting of magma, then you have the volcanoes. So those happen together. The basic working theory is plate tectonics. That's what's driving all of this. Process of uniformity. What's happened today has happened before and will continue happening. Diastrophism, how the Earth's surface is being changed, that process of deformation that these are talking about. Now we'll talk more on specifics. Let's give a little bit of the physics of it. Not too much, but a little bit. Two concepts here, and they almost sound alike. We start with the same three letters. Stress and strain. Now here's how I like to think of it, because this is just the weird way my mind works. Stress is the force. Stress is sort of the verb, okay? It's the action that's going on. Strain is the adjustment to the stress. That's sort of the object of that action, or the thing that's happening. That would be more like the noun, okay? So what is stress? The force tending. And again, catch these three concepts here. They don't sound too unfamiliar to us, I don't think. When you're compressing, pulling apart, or deforming. Boy, that sounds familiar, doesn't it? But now we're talking not plates, though it could be plates, but we're talking about actually rocks or structures, okay? Three types of stress forces, okay? They almost put them here. Compressive, pulling apart, tensional, and deforming or the shear stresses. So let's talk about, boy, that sounds familiar, doesn't it? What does that sound like? The three types of boundaries we were just talking about. Converging boundaries, diverging boundaries, and transform boundaries. Here we have the same type thing, but now we're talking about rocks or smaller areas and plates. Compressive stress. Now these are the forces. This is when the plates are moving together, just like your converging plates, when they're moving together. Those are compressive stresses. Your tensional stresses are the stresses that tend to be pulling things apart. Okay? That would be like your diverging boundaries. Okay? And then finally we have the shear stresses. Now when I say shear, it's not S-H-E-E-R, which means you can see through. This is shear like one thing's moving one way and one's doing another, and you can have stresses that way. Forces that are caused by plates sliding past each other, just like your transform boundaries. Okay? So these can relate to plates or smaller things like rocks or areas. Now, strain, you have three reactions to forces. These are the adjustments to the stresses or the forces, three strain types. All right? The first of these is elastic strain. Now, what does elastic mean to you? Okay, we think of it as a stretchingness. It's involved with that. But what makes it elastic is not that it stretches, but that it comes back to its original shape. At least we hope it does, okay? Sometimes my elastic doesn't, okay? But what elastic means is to return to the original shape. It gets deformed, but it comes back. Okay? Think of this. I mean, most times your springs are like this, aren't they? You compress the spring, but when you release the stress, it comes back to its original shape. Your springs in your car. Some cars have coil springs. Some have what they call, goodness, I want to call them plate. That's not what they call them, but they're springs that, lay on top of each other. There is a name for it. I can't think of it now. But springs, to be a good spring, is going to come back to its original shape. However, you've probably done it to some spring or another before in your life. You probably stretched it a little too much, and it didn't come back. Then you pass its elastic limit. As long as it returns to its original shape, that is called elastic strength. Returning to, this is the adjustment to the stretch, it comes back. Now, rocks can do that. You can put pressure on a rock, but then if the pressure is released, the rock basically goes back to the real shape it was. Okay? Elastic strength. The second of these is plastic strength. In this case, it doesn't come back. Oh, here may be a good example. It seems like, y'all remember the Saturn cars? Okay. There was an ad for them. I guess it was a little kid playing ball in the yard, and his ball hit the car, but the car came back. And that was supposed to be a feature of the Saturn. They were built with materials that when you got deformed, it would come back to its original shape. I don't know if that was really true. It's probably just a commercial. But I know that a lot of cars I've been in, when they get hit, they stay dented. Okay? That would be plastic strength. It would be molded or bent and not returned to the original shape. That would be that spring that you stretch a little too far and then it doesn't come back. That would be plastic strength. Does not return to the original shape. Now the third type, elastic plastic, then fracture. You put a force, a stress, on the rock, on the material or whatever, but rather than just giving a little and coming back to original shape, or giving a little but then getting deformed and not coming back, it actually breaks, cracks, breaks, fractures. That is fracture strength. Now, trying to think of an illustration of this, and this one comes to mind. It's probably not a great illustration, but if you were to watch it, I don't know if any of you are golfers. Are you? Okay, I'm not either. I played a little when I had to, but not one of my favorites. But if you watch, especially these pros, they go back on their swing, and when that golf club hits the ball, literally, if you can watch a slow motion filming of that process, you'll see that club actually bends backward like this. Okay? But then it comes back to its original shape, giving even more push to the ball, and the club is perfectly fine. But if you watched it, it actually got bent. That was elastic strength. It got deformed, but it wasn't a permanent deformation. It came back to the original shape. Okay. I've at least seen this in cartoons. Fortunately, I've never been on a golf course when I've seen it happen. But someone really loses his temper and takes the golf club and bends it across his knee or something like that. I think Charles Barkley or something like that. I don't know if he's ever done it, but that's one name that comes to mind that could do it. And that golf club does not come back to the original shape. But then, too, I guess if you really got mad and slammed it into a tree, it may have actually cracked or fractured. Okay? I'm picking on golfers because I don't like it that much. But those are three types of strength. Three types of stress. The force is the action. Three types of strain, the nouns, the reaction, the adjustment to those stresses. Come back to original shape, elastic, get deformed permanently, plastic, or break completely, fracture. Okay. Now, let's look at stresses, those three stresses. Possible material responses to those stresses. And this is almost going into the strains again too, but we'll get to it. Absolutely no change. Okay, guess what? I'm going to push on this wall. Okay, I'm going to push really hard. It's not budging, is it? Okay, I don't even think I was indenting it any. Okay, it didn't need to come back because it did not change at all. Okay, now, I'm not going to do it, but I could concede that if you really push hard enough on the door, it might give just a little bit, but then come back. That would be elastic change with recovery. Okay? If there was something metal in here, maybe this box here, I can easily imagine that I could hit it with something hard enough that I'd make a dent in it that didn't come back. That would be plastic change, no recovery. And then the final would be if I really walloped something and broke it completely, that would be breaking from the pressure. So basically, it's almost a restating of those same, now they have four, no change at all, pushing on the wall, it doesn't even dent, okay? But this is, again, the possible material responses to your stresses or your forces. Now, let's think in terms of rocks. I was thinking in terms of things in the room. Let's think of rocks. What would contribute to how the rock responds to these stresses? One thing would be the nature of the rock, okay? If you think about some of the rocks I had in here when we were doing the last lab, I think you can easily imagine some of those sandstones. If it had very much happening to it, it's just going to crumble, okay? Some of the harder sandstones may not, but some of them would, okay? That would be breaking under the pressure. So the nature of the rock really would make a difference. The ores, like iron ore and stuff, going to be hard to make much change on it. That may be no change at all. Others may have elastic recovery. Others, though, may have plastic change with no recovery. So the nature of the rock itself. What are the chemical bonds that are holding that rock together? The minerals that are making up that rock. How strong are they? How brittle are they? Okay? That's the type of thing you're asking. Next is the temperature of the rock. And we talked about near the surface, tends to be fairly cool. The deeper you get, the hotter it gets. This is a big key here. Temperature of the rock. What do you think happens with greater temperature? Say again? Yes, exactly. The bonds get weaker. The chemical bonds holding it together are not quite as strong as they were before. They will give a little bit, okay? So with the raising temperature, you're going to get more plastic change and less elastic change. Because of the greater heat, that bond is not going to return to the original shape as easily. It's going to actually get deformed. Now, in some of my other illustrations here, I was bringing this one in, the speed of the stress application. How rapidly is that stress happening? If I push so gradually on this box here, and just keep pushing and keep pushing and keep pushing, and maybe have something a little bit stronger than me and keep pushing, that's more than likely going to maybe plastically deform that. But if I take something, say a dart, and throw at it real hard so it happens real quickly, it could actually fracture it. In other words, puncture it, okay? So the speed at which the stress is applied. A gradual, slow increase may make no change, an elastic change or a plastic change, whereas a very, very rapid stress application could easily break the same rock, same material, same nature of the rock, same temperature of the rock, just how fast the stress is happening. Okay? And then the other rock variables what's going on around the rock? The confining pressure. If this rock is deep underground and is being supported on every side, then it may have no change, or maybe an elastic change. But if suddenly the overburden, the material on top of it, gives way or slowly gives way, then that rock may actually deform where it wouldn't have before. The confining pressure. Is there enough pressure above, below, on either side, or wherever to keep the rock in the original shape, or to allow it to deform and make a plastic change over time? So you see, the rock has variables that influence which of those changes, responses you might have to the stress. And then you have interplay between all these, and that could really form. So for instance, if you had reduced the confining pressure at the same time temperature was increasing, you really would have more plastic change without recovery. Okay? But if the rock was really cold, it might be quite brittle, and now you may have breaking under pressure rather than some other type of deformation. Okay? Because you know, now this is pretty gross, but they say that if you were to, I wouldn't suggest it, stick your finger into liquid nitrogen, you could do that, and there goes your finger. Yeah, that's pretty gross sounding, isn't it? But really, when it gets very cold, it gets very brittle. Okay? Whereas I can do this now, and my finger comes back close to the same. Elastic change with recovery. Okay? If that was cold enough, no, pretty gross. Let's not think of that. Okay? Now, there are ways to express this graphically. Okay? Here's a material A. Okay? Now, to me, they've got these axes backwards, but this is how they always do it, and I guess there's a reason for it. Usually I think of the independent thing, the stress being on the horizontal axis, and the result, the dependent on the vertical axis. They've got them reversed from that. Now, I guess there's a reason for it. Okay? But if you're applying a stress on this material, it is responding to the stress by moving. But it's a straight line response. You exert a little stress, it has a little response. You exert a bigger stress, it has a bigger strain. Okay? The stresses are here, the strains here. So, but as long as this is linear, or nearly linear, that's called elastic behavior. You do a little, it changes a little. Do more, and you let up, it goes back to where it was. Okay? Now, two things could happen. You can keep adding more stresses. No matter what the material is, diamond, you can keep adding more stresses to it. At some point, something's got to give. Once you get a bending, that now means you've reached the elastic limit, the straight line behavior. Do a little stress, it does a little strain. Do a little more stress, it does a little more strain. But it's all proportional. But once you pass that elastic limit, now you have plastic deformation. You do some more stress, and boy, it pings over really badly and doesn't come back. That's plastic deformation. Now, not all materials will go into plastic deformation. They may be elastic, and then all of a sudden break, rupture. So you could have, that's the B case here. Now, a little bit of stress caused more strain there. It doesn't matter which way it went, but when it reached this elastic limit, it actually ruptured. It broke. Others will go through plastic deformation first, but then you keep adding stresses to it, and then it ruptures. Okay? That would be like the throwing the ball against the car. If the fender pops right back, that's elastic. If it stays dented, that's plastic. Okay? But if you really wham it with something that actually breaks and you get a hole in your car, then that would be rupture. Okay? The material actually gives way. Okay? So that would be a rupture. Make sense? Again, it's talking stresses and strains. They say stress, but the strains of that. Now let's think in terms of rock. Okay? by the way, where are we now? Before we go too far, just to catch up in the book. In my book, anyway, on page 481, there is actually a picture of from the south side of the eruption of Mount St. Helens. I mentioned that earlier. May 1980. Were any of you born then? No. Okay. Sorry about that. I was 29 years old. Okay. So, yuck. Let's not go there. Here's a rock island with a bunch of sea lions or seals or something laying all over. That's interesting, but I don't see. Here's a picture we just had. Now we're on the subtopic of diastrophism. Interpreting Earth's surface was a very short topic. Diastrophism in 1902. And here is one of those responses to these actions. Now we're thinking rock, okay? Especially sedimentary rock. Now it's not that the others don't exhibit it, is that sedimentary rocks show it so well, okay? But sedimentary rock, generally, by their name, originate from sediments. And most of the time, sediments are flat, right? Horizontal. That's what it means to settle out, okay? Whether they're clastic sediments, which are made out of particles, or they're chemical sediments, they still basically form flat surfaces, okay? So they originate from flat sediment. The layers are usually horizontal. One layer, and then over time another layer, and over time another and another. And the deeper they go, the more, remember the two has lith in the name. Lith, rock forming process, I'll put it that way. For sedimentary rock, what two conditions go about making a sedimentary rock from a sediment to a sedimentary rock? Compaction and sticking them together. Second, cementation. Think cement. That's holding the block together. Cement. Okay? Okay? So they're usually horizontal. Now, so you have these sedimentary rocks. They formed, they've compacted, they've cemented, they're hard rock, okay? But then you got pressures, say from below or lose pressure from above, heat, whatever is happening, and then you have bends in the layered bedrock, okay? We'll see some pictures of this in just a second. In fact, let's show one now. Here's one. Bending. You've got some sort of pressure coming up here, that convective pressure from way down in the asthenosphere or somewhere like that, pushing upward, okay? What was flat is now being bent. These are called folds. Bends in the layered bedrock. These are folded mountains or folded rock. Result of stress produced by plastic strain. The stress came up here, the rock got bent, it did not return to its original shape. Plastic strain. Generally, widespread horizontal stress can produce a dome or a basin. It depends on whether it's a positive stress or a negative stress. Domes or basins. Okay? Now, when I see or think this, I don't know if I'm right on this or not, but I think Stone Mountain. Any of you ever been to Stone Mountain, Georgia? Just east of Atlanta? One huge granite rock outcropping. And when I say huge, I mean really, really big. It must have been just some huge stress that forced that up from way underneath. It's granite, igneous rock, but I don't know if that's what it's from, but I think of that sort of your dome. Now think of other things like, have you ever driven by fields and seen some low-lying area and maybe water standing in it when it's rained recently, but not always? Those are sometimes called Grady ponds. That's happened when the limestone or calcite or whatever is underlaying it, chalk mostly, underlaying it has chemically eroded away, and so the pressure is reduced underneath, and that makes these basins, okay? And fields where I grew up on a farm in Georgia, and we had some fields with these in them, and we had neighboring fields with them, and just places the soil was just low, and didn't seem to be any reason for it. What was underneath there had given way, and you had basins for it. Now, other times, if they're more directed, I guess you would say, not widespread, but more pointed, then you have this. It's called an anticline. Think arch. Anti-arch, okay? When the pressure is from below and it forms an arch like this, okay? That's called an anticline. On the other hand, more like the basin, when something's given way underneath, that would be called a syncline. Now, there's no alliteration here that I can use for that, but it's just the opposite of anticline is syncline. Okay, that's been a drop. Now, I don't think they have a, do they? Yeah, here's a syncline. For some reason, you have a reduction in pressure here. Perhaps the chalk is eroded away, or, and they do have these around here quite a bit, sinkholes, okay? Yeah. Awful lot of roads I've driven on, I wonder if there's sinkholes on them. Actually, our neighbor's yard, in her front yard, the soil just keeps dropping. I don't know if there's an underwater spring under there that's washing away soil and then it lands. Their boy, one year when he was young, he raked up all the acorns in the yard, and we have a lot of big oak trees. He asked if he could, yeah, you can use our acorns. And he was filling the hole with acorns, you know that's not going to last. But man, he got, not tons, but lots and lots of acorns to fill it up. That was more like a basin. This is a syncline, okay? Something is given way, or pressure's on the outside, usually something given way underneath, and you have not the arch, anticline, but the maybe sunken middle, which would be syncline, trough-shaped structure, okay? So, those were folded mountains, okay, or folded structures. Bends in the layered bedrock, okay, no, that's the same thing we had before. Thought, why are they showing it again? Is there something else they're wanting to show? Here's some. Here's some actually pictures, not illustrations, but pictures. What does this look like to you? What kind of rock do you guess those are? Just looking at the picture.
I'd say the top one's sand.
It's what?
I think the top one's sandstone and the bottom one's white.
Okay, possibly, but look at this. Everything's in horizontal layers, aren't they? I would say all this is sedimentary rock until somewhere you get down here, it may not be. It may be igneous rock somewhere under there. But everything that is flat like this, that's sedimented on top of something, on top of something, on top of something. Those are all sedimentary rocks. Almost guaranteed. Now, you see that one time, this was also sedimentary rock, but what has happened here? You have a bending upward. What would you call that? Very small one, but that would be an arch. Arch, which is called an
Anticline.
anticline, exactly. Okay? These are also sedimentary rock, but you see there's uneven pressure because all the rocks are in layers. But now the layers aren't horizontal anymore, there's been pressure. I don't know, could this be a
Side syncline.
syncline? That could be a syncline. I don't know, I don't see enough beneath it to suggest that, but it could be. Okay. Thought of something else, but it flew the coop, so we'll keep going. An even bigger one. Okay, what you reckon? This is obviously. Oh, I remember what I was going to say now. That's obviously was sedimentary rock because you can see the layers there. But something has happened and you folded or bent the rock, and this would make a big this would be an anticline. This would be the syncline. Okay? Big scale there. And look at those cars and look at that. Now, I really enjoy driving up 65. My wife's from Huntsville area, so we drive up 65, a few times a year to see her family and stuff like that. I really enjoy driving up 65 just to look at the road cuts through there. And there's some places things are fairly flat, not too many. Sometimes those layered things are like this. There have been some major shifts going on there. Sometimes they're not nice and rounded like this, and we'll talk about that in the next thing we talk about, but that would definitely be an anticline, a syncline. There's been some folding going on here, some major, major folding. That had to result from plastic behavior, okay? Now, my suggestion is that was way deep that happened, because you don't have that kind of folding unless you have a fair amount of heat that enabled that rock to deform like that, okay? My guess that was that, okay? Now, this is sort of backwards here. This is more your domes and your basins. These are both domes here, or illustrations of domes. When the center part is raised up, this is your oldest rock here because it came from very, very deep. I'm not seeing this too much. I don't think this is matching very well. But then the next older ring here and here. What has happened, this used to be a dome, but then it's eroded away, and that leaves a variety of types of rock here, but the oldest being in the center and the more recent being along the edges. And this is a dome structure with a lot of it has eroded away, and I'm pretty sure this is Sundance, if I remember right, which, it may not be in this edition. I think this was in an earlier edition. Okay, so I don't have that for you, but my memory is that was Sundance Mountain, but I'm not absolutely sure. Okay, so those are your folded structures: domes, basins, anticlines, synclines. Okay, I don't know what was supposed to have been there. Must be some more illustrations they just didn't quite get in here. But let's now go to faulting. Folding is basically plastic activity. The stresses formed folds, not breaks, but folds in the sedimentary rock. The other kind of activity you can have is faulting. Okay? Now, the book makes a bigger point than the slideshow does, so I want to make sure you understand it. There are two things that happen here. There's a fault that's produced by relative movement on opposite sides of a crack. So we have a crack. Why the crack occurred, we don't know. Stresses, whatever, fractures, whatever. You had a crack. Now, the crack is there. If you have no relative movement between the crack, and the book mentions this, they don't mention it on the slide, that is called a joint. You'll see that on my page 484, depending on which edition you have. That very first paragraph under faulting, you'll see in italics, a joint. Joints are common in rocks exposed. Okay, I'm sorry. The sentence before that. A sudden stress on the rocks may reach a rupture point, resulting in cracking and breaking of the rock structure. If there is breaking of the rock without a relative displacement on either side of the break, that crack is called a joint. So that's one kind of crack. Okay? We're going to be talking about the other kind, faults. That's produced when you do have relative motion on the opposite sides of the crack. One's going to go up, the other go down, or something of that nature. Now, when you have that, and let me get a picture of it. Now we're talking about faults as opposed to joints. Joints are no relative motion. Here we have an example. Here's your crack. Here's the crack there, okay? Now, the lower side of that crack, the crack is always at an angle, the lower side is called the footwall, okay? The footwall block, they call it here, okay? The mass of rock that's below the fault. Now, the fault isn't horizontal, it's always at an angle, but the mass of rock below the fault is called the footwall, and then the hanging wall is the part that's above the crack. Even though the hanging wall has slid down, it's still hanging. It's not meaning it's hanging up, but it's a hanging wall because it's the part above the crack. Okay? The mass of rock above the crack. The crack itself is called the fault plane. That's the surface between the footwall and the hanging wall. Footwall and hanging wall, that's the fault plane right there. Okay? Got the terms down? Now, you can tell a lot by paying attention to this. Okay? For instance here, what can you tell me? What seems to have happened here? Both that picture and this picture. That's an illustration. This is actually a picture. The hanging wall slid down the footwall, right? Okay. That tells you something about the forces or the stresses that cause this. These had to have been tensional stresses pulling them apart to make the hanging wall fall down. If it had been stresses that were compressional, it would have been pushing the hanging wall up. Okay? But you can tell this has gone down because you see this streak here, that used to line up with that streak. This band here lined up with that band. Okay? You can't see much else, but that's certainly enough to give you a clue of what was going on. This tells you something about, this is a fault, not a fold, okay? And it was caused by tensional stresses, okay? So this leads to these classes of faults. The normal fault, that's what they call the first class, when the hanging wall is moved down relative to the footwall, like we just saw, it slid down. The related features of this, and don't sweat these. These are just words, but they're nice words to know and recognize and understand. I wouldn't try to memorize them, okay? The graben is the block that's surrounded by normal faults. Drops down, okay? So this would be the graben, okay? The normal fault, which of course, and as I mentioned before, caused by tensional forces here. Now here is this first. The hanging wall has moved down relative to the footwall. This is the footwall, it's below the fault. This is the hanging wall, it's above the fault. Even though it has slid down, we still say it's above the fault because it's on the upper side of that fault line. Okay? So this is a normal fault caused by tensional stresses. Okay? But when you have a block surrounded, and both of them are normal faults, the hanging wall has dropped between the two footwalls, one on this side and one on this side. That's called the graben. The block surrounded by normal faults drops down. Okay? However, if you had in the middle your footwall and you had hanging walls that fell down on either side of it, because this is the footwall, so the lower side here, lower side here, hanging wall here, because it's on the upper side of the crack or the fault, then the block surrounded by the normal fault is uplifted. Okay, not really uplifted. The other two have fallen down. That's called the horse. Okay? And Terry's here. Catch the time. Yeah, you made it in to the first part. So Terry's here. Has anyone else come in since I originally called roll? I haven't noted anyone, but so we're still missing Darius, Bianca, James, Carrie. The rest are here. Okay, good deal. So that's called the horse. Okay? I don't know. Oh, I say it, and then he shows up. Okay? This is your usual seat, but you can sit anywhere you want to. I probably need to sit anymore. Okay. There it is, sure. All right. So we're just missing Bianca, James, and Karen. All right. And we're gaining and losing them all the time, it looks like. Okay. So Graven, I don't know. Round down, I don't know. Horse, up on a horse, I don't know. I wouldn't sweat it. Not worth wasting the mental effort to memorize. Okay? There are other faults. You have many other faults. No, I'm sorry, that's not what we're talking about. The normal fault is when the hanging wall slides down the foot wall, but a reverse fault is when the hanging wall is moved up relative to the foot wall. Now, what must have caused that? Compressional forces that forced it up. Tensional forces allowed it to slide down. Compressional forces forced it up. That would be a reverse fault. Now, there's another kind. It is also a reverse fault, but it's one with a very low angle fault plane. So let's see if we can get some illustrations of that. This would be a reverse fault. Here is your foot wall, and obviously the hanging wall is now moved upward. That had to be from compressional forces. But if this same structure here, foot wall underneath, hanging wall up above, is a very shallow angle here, that's called a thrust fault. It is a reverse fault, but with a very shallow, low angle fault plane. Okay. Now, things about here, quite often you'll see a pretty big divide here, like a hill or something else. Here is a much more gradual thing if you notice anything at all. In fact, that's so gradual, it may be that things have eroded away as fast as it's happened, and you don't even notice the change, or a very, very small change. Now, faults provide information on the stresses producing the formation. Here we see it, and on the last one they had the arrows, but they didn't say it. I said it and put the words in there, but what kind of faults are caused by tensional forces? Second? What kind of faults are caused by? These are the. Second? Yeah, tensional forces. They produce what kind of fault?
Folding?
No, folding is when you have bending, not breaking.
Hanging.
Second?
Hanging.
Okay, the hanging wall has slid down the foot wall. What kind of fault is that? It's not Abby normal, it's normal. I'm sorry, that was from the Young Frankenstein movie long time ago. Okay. Normal faults are when it slides down. Reverse faults are when it's pushed up, caused by compressional forces. And a gradual compressional force or reverse fault for a low angle, that's a thrust fault. Okay, so they let you know what kind of forces created them or contributed to them anyway. I'm going to have to sneeze, I'm afraid. Y'all wake up. Sorry. Okay, getting there. All right. So now we move in. There's a couple of examples here, and let me get a couple of other issues here. They have some weird pictures in weird places. I mean, pretty pictures, but in weird places. When they're talking about the columnar jointing, okay, there's those joints again, so this is the right place. The cracks occur, but there's no relative motion. So when there's cracks but no relative motion around the crack, that's called a joint, not a fault. Okay? The figure 19.9 in my book, That's sort of a weird one because the fault plane is almost vertical. Has a slight angle over, so the one on the underneath side of that slight angle is your footwall. The hanging wall is above it, and it looks like the hanging wall has been pushed up, so that was compressional forces. Rather strange. Now, there's a concept applied here on making clay or plaster or paper mache models to illustrate faulting and folding. If you're interested in doing that, knock yourself out, go for it. There's a couple of examples here, and I mean, there's sometimes, I mean, these are fine examples and stuff, but it's sort of like they make up a problem to give you an example. Not something that I can see you'd ever really need to know. It doesn't really, it does support a little bit what they're talking about, but not so much. But now we're moving to 19.3, which in my book is on page 486. And that's moving in the concept of earthquakes. We mentioned them in the last chapter, okay? We'll mention them, I'm sure, later too. But just getting what this is, an earthquake is a quaking, which means a shaking, vibrating, upheaval, whatever you want to call it, movement of the ground for whatever reason. The ground is moving, heaving, shaking, vibrating. That's an earthquake. What causes that? It results from a sudden release of energy from stresses on rocks. So here you've had the stresses, which are the forces, pushing one plate against another, one rock against another. It could be subducting, as in convergence boundary. It could be moving past each other on a transform boundary. Either of these, just movement of rock relative to another. Whatever the reason for the movement, it's been pushed, but it got hung up for some reason. And it's stuck, but the pressure keeps increasing. The forces keep increasing slowly, gradually, and then suddenly something gives. That sudden release of energy, usually caused by a fracture somewhere down the line, or something like that, from that stress on the rocks. The stress is the force, the strain is the reaction. Probably that strain was a fracture. Now, the vibrations that move through the earth are called seismic waves. Now, we talked about this some in the last chapter, wasn't it? When we talked about the makeup of the Earth's core. Didn't we talk about seismic waves? The three types of seismic waves. Two of them referred to by letters. One stands for primary. P waves and S waves, exactly. Primaries are pressure waves. They are the fastest moving waves. They are the longitudinal waves. What is a feature of P waves, primary waves, pressure waves?
They can go through liquid.
They'll go through solids, liquids, gases, anything. They go through solids and fluids. Let's classify liquids and gases as fluids, okay? Now, so just trying to remind you. Then the other type is second type of seismic waves. Secondary waves, also called S waves. Another S word is shear waves. Okay? It's not longitudinal, it's transverse. Okay? Or shear waves. Those are slower, also S, than the primary waves. Okay? And not only that, what else? Other feature of transverse are they will not move through a fluid. They only move through solids. You're absolutely right. Okay? Now, the third type was what we call surface waves. That's after it reaches the surface, you get that. Those are all seismic waves. Those vibrations create those three types of waves, all seismic waves. Most occur along the fault plane. Not all, but most occur along fault planes when one side is displaced with respect to the other. The fault planes are there, and something gives. Now, these are not always your plate boundaries. Remember that. They could be interior. But they still have all these pressures that come about because of plate tectonics. It's just that they're within a plate, not at the boundaries of plates. Give you some examples of this. Not too many years ago, I'd say fewer than 10 or 15, there was a reasonably, not super powerful, but reasonably significant earthquake somewhere not too far from Washington, D.C. I think it was either Virginia or West Virginia or somewhere, far from a plate boundary. But there was still an earthquake there. Something gave. There were pressures there, and something gave. You had an earthquake. Why I know it was near Washington, D.C., a pretty significant structure in Washington, D.C. was damaged. You know which one it was? The Washington Monument, that tall obelisk, the spire that's there. Nothing can be taller than the Washington Monument. That's why all the buildings in D.C. are fairly short. Nothing can be taller than the Washington Monument. It used to be you could go up the Washington Monument and see the whole city from the top. They had to suspend those tours until they got it repaired and reasonably sure it was safe for people to go. I think they've opened back again. But another thing I remember from that, over here in Alabama, I felt nothing. I didn't hear of anyone feeling anything. But over in Georgia, the farm that I grew up on in Georgia, when my parents died, it was split among the 4 kids. And on my portion, we built a little 2-bedroom bungalow. So when we go over to visit our family or do something that we have to take care of on the farm, we'll have a place to stay, and we don't have to move them around and bother them, especially if they've got the kids or something home. So we just built a little place over there, and it was only been there a year or two. I know my wife's sister had given her, because it's in the middle of a cow pasture, had given her a little thing to put on the wall that just said farm. I mean, it was a nice little wall hanging that said farm. And we came one time and walked in, and the farm sign was down on the floor. I thought we did a better job of hanging it than that, and everything seemed to be in place. The nail was still there. It hadn't fallen out. Everything was in place. So we said something to my sister-in-law and said, wow, the sign fell off the wall. She said, oh, that must have been when the earthquake happened. So the same one that was damaged the Washington Monument in Washington, D.C., in middle Georgia, it was still felt. Just a small tremor, but she said she noticed things moved in her house too. So she said it must have been the earthquake. So those seismic waves travel quite far, even for very, very minor earthquakes. Okay? Most occur along those fault planes when one side is displaced with respect to the other. That's what an earthquake is. A shaking when there's sudden release. Now, I keep thinking of this thing. It's come to me a time or two, and then when I don't say it, I forget what I was going to say. Let me go back and see if I can remind myself. I think I said it. Okay, I said about the driving up 65 and looking at the various rock formations there. What are some of the causes of earthquakes? Well, relative motion of plates or rock formations, okay? Here's one theory, the elastic rebound theory. Now, earlier I said something fractured. This theory doesn't have it necessarily fracturing. It may be that it bent, it gave, and then slid past each other, but then rebounded. It was elastic, not fractured. So this is the elastic rebound theory. 2 plates press tightly together, the friction restricts the motion, the stress builds up until the friction or rock, and this says rupture now, not elastic, okay? The rock rupture strength is overcome, the stress rock snaps suddenly, into a new position or gives way and snaps back to its original position. That would be elastic rebound. What they're describing there is rock rupture, which is not elastic rebound, but rebound, nevertheless. Okay? So that would be one theory, cause for earthquakes. And guess what we have here? The good old San Andreas Fault. Notice it goes inland. It's east of Los Angeles, a little bit north of it too. But still, when there was an earthquake anywhere along here, Los Angeles felt it big time. I can't remember how long ago that was, but it wasn't many years after the San Francisco quake that was a World Series quake. And looking at this fault, now, if this is indeed true, the Bay of California is much more to the west here, but I'm wondering if that line is absolutely correct, if it doesn't fall down into that. That would be my guess. I may be wrong on it. But you see, San Francisco Bay almost makes you wonder if that didn't become the bay there as a result of some big eruption sometime in the past, or earthquake sometime in the past. We've known of two major quakes in San Francisco, like I said, one at the end of the 19th century, beginning of the 20th. And actually it was a pretty major earthquake, but far more deaths came about by fire. Because when an earthquake happened, gas lines ruptured, and they caught on fire, and most of the buildings were wood, and they burned like crazy. So it was, back when it was a pioneer town, sort of, it just wasn't prepared for it. Okay? But then somewhere not too far past San Francisco, it moves on out to sea. And it basically forms the boundary between the North American plate and the Juan de Fuca plate up here. Pacific plate down here, Juan de Fuca up there. And it makes you wonder if maybe some of these other features you see here were shaped by that San Andreas Fault. Now, the book also mentions another fault. Let me find it for you quickly. It's on page 486. It says, most earthquakes are explained by the movement of rock blots along faults, but there are other causes. Earthquakes have occurred in the eastern U.S., like the one I was talking about, without any apparent relationship to known faults at or near the surface. One of the largest earthquakes on record in the United States occurred not in California, not along the San Andreas Fault, but in a region of New Madrid, or Madrid, I don't know how they pronounce it there. Spain pronounces it Madrid, but someplace in the U.S. call it Madrid. Missouri. Missouri? Right in the middle of the U.S.? New Madrid, Missouri. Missouri is, if I get enough light to see it here, oh, this doesn't divide the states very well, but it's right over here. There's the Mississippi River. Missouri is right in here. Way long distance from San Andreas or the East Coast or anywhere. One of the major earthquakes on record was there. Now, why, we're not absolutely sure, but you see, again, I think there could be some weaknesses or disturbances in the middle of a plate, just like there are on the edges. Most of them are on the edges. Now, the interesting thing about the New Madrid or New Madrid fault, I think they pronounce it Madrid, was that it was so major. Like I said, Missouri bound is border on one side is the Mississippi River. In fact, the Missouri River comes in right at St. Louis and joins the Mississippi. It came down from Minnesota to form the big Mississippi, because actually Missouri has more water than the Mississippi did until it turned into poured into it. But here's the deal. I don't remember how many, does it say in the book? The quake toppled chimneys 400 miles away in Ohio and was felt from the Rocky Mountains to the Atlantic coast from Canada to the Gulf of Mexico, the new Madrid fault zone is theorized to represent a failed rift that is being reactivated by compressional stresses in the from the west and east. Okay? Now, they don't say here, but I know I've read before. I just don't remember how long. But it was such a major earthquake that the Mississippi River flowed backwards, flowed upstream for a few days afterwards. I don't remember how long, but it actually was that big. And if you've ever crossed the Mississippi, that's a lot of water, a whole lot of water. And it actually flowed upstream. There was that big of a quake. I can't imagine it, okay? Now, obviously, we had settled the U.S. by then, but fortunately, nothing has happened since. Now, my question to you, what is better? Lots of little quakes or one big one?
One big one.
Sort of hard to say. The one big one is going to cause untold damage. Lots of little ones you can survive, like the one that was in D.C. Yeah, they did some damage to the Washington Monument. No buildings fell down. The hanging came off the wall, but nothing major. But something like that new Madrid, or however you call it, if there had been any buildings anywhere close by, they would have been totally destroyed. Okay, I don't know what phase of our history and how much development we had done then. That would have been major disaster. Now, so you can't always tell. Not too many years ago, probably during your lifetimes, there was a pretty major earthquake in Haiti. Do y'all remember that? Right around Christmas one year, wasn't it? Right after Christmas, I believe it was. Enormous amount of damage. Why? Was it that big a quake? Not really. It's just that in Haiti, they had very, very poor building codes, building standards, and most of their structures were not designed or built to withstand anything. So when it hit, even though it was a fairly minor earthquake, it almost destroyed the entire city. And it seems like to me within just a few months of that one, there was a much bigger earthquake in Chile. But you know, Chile's right there on the Andes Mountains, you know, that's the ring of fire. There's so much activity going on there. They were prepared. They knew they had to build their buildings to withstand these things, and much less damage, even though the earthquake was much bigger. Okay? So sometimes the size of the quake, oh yeah, that matters. But sometimes our preparedness for it, for instance, the Bay Bridge Tunnel in San Francisco, that should have been built much stronger than what it was. You're on the San Andreas Fault, folks. You know, you should build things that can withstand it. In Japan, they built a nuclear power plant. In fact, we've done it in the U.S. too, right on the fault. The Fukushima nuclear, almost major disaster. It was pretty much a disaster, but it came as a tidal wave right after an earthquake. So, sometimes it's the earthquake's fault, sometimes it's our fault for not paying attention to the conditions. So what are the causes of these earthquakes? Again, here's that theory again. This is the picture I thought knew was coming up. This to me is an incredible picture. The San Joaquin Valley in California is one of the richest agricultural areas in the country. They have to do lots of irrigating there, but you know, it's very rich soil. Lots of great growing conditions. But guess what? Part of it's right on the San Andreas Fault. And after one of those quakes, I don't know which one it was, whether it was the one in San Francisco or the one in Los Angeles, but after one of these, look at that field. You can tell where the fault line is right there, because the rows were lined up, and after the quake they weren't. What kind of boundary is this? Transform boundary. They're moving, sliding past each other. You can tell that big time right there. I've never seen a picture illustrate that better than this one. Okay? Here is their representation of it. You got stresses on both sides. Transform boundary, there's shear stresses. They're trying to slide past each other. So one's pushing this way, one's pushing that way. Say the American plate's pushing that way, the Pacific plate, or the one diffuser plate pushing that way, sliding past each other, transform boundary. It pushes, there may be a little bending. Now you don't have roads that bend like that, but maybe they almost did right before. Now they don't ever move that much. They move like this. That's maybe 8 to 10 inches, okay? Nothing, a whole lane of traffic, not that. But the earthquake happened, and when it did, it released all that stress that you had there, and it gave way suddenly, okay? The elastic rebound theory, which I think really should read fracture rebound theory, to keep the words right. Now, locating and measuring earthquakes. This is the bottom of page 486. Okay? Yeah, we're getting close. Here's a few terms you need to know. The focus is the actual site of the seismic waves. That's where the actual earthquake occurred. That's where that rock that was holding, that finally gave, that's the focus of the earthquake. Generally, way down deep. They're not on the surface, way down deep. But on the surface, we call it the epicenter, the location on the Earth's surface directly above that focus. That's where most of the energy is experienced on the surface. The focus is where it actually occurred. The epicenter is on the surface where most of that energy focused. Now, there is a device. When you see the suffix graph, that means to mark, so it graphed the earthquake. The seismograph. It measures and records the seismic activity. It's the instrument used to detect and measure the earthquakes. Okay? It detects just because it vibrates when the earthquake happens. Okay? Let's see if there is actually a picture. I think there is. No. Okay, this is showing the focus. The focus is somewhere way down here. The seismic waves move out from this. The epicenter is the first place where the seismic waves reach the surface. That's the epicenter. And then they spread out this way. They're P waves and S waves here. On the surface, they become surface waves. Okay? Now, this shows one from what kind of fault is this one? Remember, there's 3 types of faults. Which kind is this?
Normal fault?
That's a normal fault because the footwall is on the lower side, the hanging wall on the upper side, the hanging wall has slid down the footwall. What kind of stresses produce that?
Tension?
Tensional stresses, pulling them apart, that's enabled them to fall. Probably they had been going on for quite a while, but something was hanging up, keeping it from happening, and suddenly it gave way. That elastic or fracture rebound happened, and then it gave way. The seismograph measures what 3 types of waves do we have? P waves, which means primary, which also means pressure, compression waves, longitudinal waves. The second being the S waves, which means secondary, which also means shear. Okay, and these are transverse waves. Okay, and then the third type of waves are surface waves. These are sort of up and down, back and forth waves that you have there. The P waves, longitudinal, pressure waves, the S waves, shear waves, are transverse waves. Okay? Now, seismograph measures all 3. Now, the P waves get there first because they're the fastest. The S waves get there next. The surface waves actually probably shake the seismograph more than the other 2, so they will look like they're the biggest. They really aren't. They're just all on the surface. They're not coming from, they came from down below, but that's when they reach the surface, they will really shake up the seismograph. Let's see if they have a illustration of that. Yeah. And this is on your top of page 488 or somewhere thereabouts. All right, and basically what it is, the seismograph is firmly fixed in the bedrock of the earth. Okay, it is attached, it's drilled down, it's part of that. Now, usually, there could be little vibrations and things like this going around, and usually the paper, see, the pen just stays where it is, the paper keeps rolling and rolling and rolling and rolling. It uses a lot of paper, miles and miles of paper without anything happening, but then all of a sudden, that means the ground is moving. And what you have here is a heavy weight here. The inertia keeps it from responding too quickly, but it does then make a measured response. This would be the P wave, the very first part. Somewhere later you'll see an S wave, and then somewhere later you'll see the surface wave. Okay, that's how a seismograph works. Revolving, paper-covered drum that is always being marked. I don't know if they actually show here. They show in your text, and they don't show here, and you'll see a flat, pretty much flat line. There's always little vibration. Then all of a sudden you'll see the first P waves hit. And then you have to be really careful. Then you'll see a little bit stronger wave, and that's the S waves hitting. And then the real big things, not that they're any bigger, but now they're all on the surface. Those are your surface waves hitting. Okay? Pretty good thing. The others are measuring other parts of the, recording from other parts of the earth, and they're not noticing it. So that means you're the one closest to that seismograph. To the earthquake. What is the place where the actual earthquake occurs? Come on, team, focus. Oh, I'm sorry, I gave it away. Okay. It's the focus of the earthquake. What's it called right above that on the surface?
Epicenter.
Epicenter. Very good. Okay. Now, so this is what we've just been talking about. In fact, maybe it's going to show here. I know what it's going to show. Now, I don't know if you noticed on the slide earlier, it says these seismographs measured the earthquake, that's how much vibration, but they also located the earthquake. How can this seismograph sitting right here tell me where the earthquake is? It can't exactly, okay? But it can give you a clue, a very major clue, okay? As we've already said, P waves travel faster than S waves, okay? So, let's say that one of you, this is hard to believe, but let's just imagine that one of you can run faster than me, okay? I know it's a stretch, okay? So what if we took off at the same place, at the same time, and started running somewhere, but you were a little bit faster than me. Now, 10 feet away, I wouldn't be far behind. 10 miles away, I'm going to be much further. I'm traveling at the same speed, you're traveling at the same speed, but now the distance is much bigger. So, using that, since P waves travel faster than S waves, the difference in the arrival times between the two on those seismographs, the P wave shows up here and then later the S wave shows up, the difference in time, and boy, these are calibrated for time as well as displacement, that time difference there, they know exactly how fast that paper is turning, exactly. How far that is, the difference in arrival times correlates to the distance from the earthquake. So, what that tells us, the difference between the P and the S wave arrival, how far away that earthquake was. But what does that tell me? That tells me, let's say it's 100 miles. It could be 100 miles west, it could be 100 miles east, it could be 100 miles anywhere in a huge circle. Hey, That doesn't tell, it tells me the earthquake's 100 miles away, but it doesn't tell me where. Okay? So here's what we got. The P wave's coming in first, S wave's coming sometime later. The difference in the actual arrival, this is time, that's the distance. The time difference here tells you how far it is from the earthquake. But you gotta have at least 3 seismographs recording that quake before you can pinpoint it. Because this first one, let's say it was this one that was 100 kilometers away, here's where the seismograph was. It knows the earthquake is somewhere on that circle. A little bit later, not much later, this reporting station here measures the earthquake, and its differences tells us it's 150 kilometers away. So now that puts the earthquake either here or there, but we still don't know which. Until we get that third site in, and it reports that it was 200 kilometers away. Well, it could have been either here, here, or here, but the only one that hits all 3 is this place here. That's where it is. So you have to have at least 3 reporting seismographs to pinpoint where the earthquake was. So guess what? One of the most successful international agreements has been the placement of seismographs at strategically located positions, hooking the data up, consolidating it so everybody can read at the same time so we can figure out where earthquakes are. A few countries have sort of regretted they were part of that. Not because they didn't know where earthquakes were, but when they were trying to do secret nuclear testing and they weren't supposed to, that creates PNS waves. And suddenly everybody knows, whoops, that was either an earthquake there in North Korea or we didn't notice any earthquake. We think they set off a nuclear test. And sure enough, we've been able to detect most nuclear tests, major ones anyway. Okay? And that's how they do it. So one seismograph can just tell you how far away by the difference between the P and S wave time difference there. That tells you how far from the earthquake, but you need at least 3 seismographs relatively close to each other to pinpoint exactly where that earthquake was. Okay? Does that make sense? So, not only can they tell you that there was an earthquake and relative strength of that earthquake, but actually with enough of these, and they have them by international agreement, where those earthquakes were. So how do we classify earthquakes? Well, basically on how deep, is it time? Yeah, it is. Yeah, right, when we were having fun. Well, we're always having fun. So let's stop here and drop my pencil. And this will be classification of earthquakes. We've measured. Where is classification of earthquakes? There we are. Same place I stopped last time, or one time in the past. Okay? So this is around page 487, those of you who have books like mine. Okay. If you need to take a break, it's going to take me just a few minutes to, number 1, go down and get the labs that she didn't have copied this morning. Number 2, I've got a little bit of setup to do. And before we do anything, I'm going to pause the screencast-o-matic. All right, we're recording again. We're ready for the lab now, I think. And like I said before, this lab, as you see, is fairly short. We've got to do a few minor modifications for what the directions say, but it's pretty much going to be as according to this. Let me say this, though. What we're going to be doing at first is on the back page, which is measuring mass, volume, and calculating density. Did anyone bring a calculator today? Huh? Oh, someone has a calculator. Oh, yeah, your phone, if you know how to use it, and it's real simple math, so just the simplest calculator on there will work. So that's what we'll be doing. That's only 6 points worth there. Then, if you turn back to the middle, after we've done that, then you have results, 4 questions. That only adds up to 10. So 25-point lab, so the next 15 points will have to come from your questions at the end of the chapter. I already pointed them out to you. There were 16, what was it? Oh, what do they call that? I can't think of the term for it now. Questions for thought. 16 questions for thought, 4 for further analysis. Okay? Or you can do some of the Part B parallel exercises if you choose. Okay? Now, I say do 15 or more of those questions. Why do I say or more? Yeah, to study for the test is one very good reason to, but another reason is, what if you miss one? Then you might only get 24 out of 25 or miss a couple or something. If you do more than 15, if you get at least 15 right out of how many you do, then you get your full 15 points out of that, and hopefully you'll get the 10 points out of this. So let's get started. You've already read about igneous rocks. Can someone name a couple of kinds of igneous rocks? Basalt is one, and granite is the other. Y'all been reading your lab. Good for you. Materials, here we have a balance or a scale. Okay, we're going to be using that. We have an overflow can. That's what the white can is. We have a graduated cylinder. We have 3 of those, different sizes. Okay, ring stand and ring, and that's what this is holding this up with. Now, I'm not using a thin nylon string. This is where I'm deviating a little bit. Y'all are going to be very careful when you do this, aren't you? A beaker. Actually, we got 2 beakers here, one up here, one down here. Okay? And a granite specimen. And if you doubt it, there's written on the side. It's granite. I agree with that. It's sort of a dark granite, but it's more brown than it's black. So this has more plagioclase and orthoclase and that kind of stuff in it. And a little bit of iron, but mostly siliceous material. Silicates. All of them silicates. Okay? And then the basalt specimen, that's the pieces I showed you before. This is what we use in our bathroom. You can tell it's fine-grained basalt, dark color basalt, so it's more than likely high iron content. So we think this is basalt. This, we're pretty sure, is granite. So what we're going to do is to use the balance to find the mass of the basalt rock. So somebody come up here and use the balance to determine the mass of the basalt rock. Anyone will do. Not all rush at once. All right, here comes Karen. First thing you need to do is zero your scale. So you know you're measuring from 0. Someone has monkeyed with that one, so you have to adjust it so you zeroed the scale. It's on 0? All right? Okay, now put those 4 pieces of basalt on your scale. Okay, now read the mass. The mass is measured in grams. Each little bitty mark is 1 gram. Say that again?
Yeah, but look like 60.
Okay, 160. This is 160, 200.
Oh, okay. Okay, yeah, 160.
160 on the nose, or?
No, like 160. I look like 162.
162?
Yeah.
162 grams of basalt. That goes on the top left-hand corner of your table on page 338. 162 grams of basalt. Okay? Now, since we got the scale here and running, someone else come measure our granite. Okay, anyone will do. Be sure you zero again first, just in case, because you know how you're reading the scale 0 for where you're going to read. Put the chunk of granite on. What you got?
450 on the
450 on the nose. Okay. 450 grams is your granite mass sample that goes underneath the basalt. All right. Now, to do the volume measurements, what we need to do is, and I've got to sit up here to do it, and I hope I'm recording here. I know I don't want to get my computer too close because there could be a little bit of spillage here, and I don't want my computer rained on. So I'm going to hold this in place because this will tilt, and someone come up and start pouring this water into this container. Anyone will do. I'll let somebody else. You did your work. Okay, here it comes.
Sorry.
Yeah. Obviously won't quite fill it, but all the way. I want to continue or get somebody else. Okay, I'm going to take that water and fill it up the rest of the way. You might need more than that. All the way up to the top. Are you at the top? Maybe a little more? Are you still? No? Oh! Is that actually spill over or?
Yes.
Okay. All right. Did y'all notice? Looks like she overfilled, didn't she? Except the water's still in there. What causes that? Anyone know? This is not to do with this lab, but it is physics. The surface tension of the water. Those water molecules hang on to each other with a fury, and they won't let the others spill over the edge until they just get too heavy and do it. So that is now, okay. I'll make sure that was empty before we begin. Okay, so what we're going to do now is the basalt rock, and someone else can do the first if they want to. Who wants to be the first guinea pig on basalt? Okay, come on. Now this is where they said the string, but I found the string isn't any better than your fingers. So take one of the pieces of basalt. I would say one of the bigger ones to start with. Okay. Now lower it very gently, holding on to just one corner of it into this water. Okay, yeah, you want it to spill over. And then when it gets near your finger, release it. Okay. See, it's hard to measure the volume of that thing exactly, but what we can do is measure the volume of the water exactly by measuring how much water we displace. Someone want to do the second piece? We got plenty of people. Come on. Okay. Thank you. You might come back and do something else later. So I'll do all these pieces because he measured the mass of all the pieces. Okay. All right. Someone wants to do one of the little ones? Okay. 1, 2. Okay. Okay, back up a little more. Yeah. A little bit more. All right, here it comes. Get the salt. Okay. Pour it very slowly and gently into the water. Yeah. And release. Yeah, okay. All right. And someone want to do the last piece. Thank you. Come on, one more. Yes. Okay. That sounds just, yeah, that one you just get in the water and then drop it. Okay, good deal. Okay. Now we need to measure how much is in there. I'd like you to take this and dump it in the sink. Get as much out of that. It's not going to get much. You just get all out of there you can. Okay. So what you're going to do, I'll do this in stages sort of, pour this water into there. That's all the water that was displaced, meaning the same volume as the water in there. Okay. The reason I had you do that is this one has a spout on it. So if you'll take that and pour it into here, you can control your pour a little bit better. We're going to get the volume of water displaced. Got it all in there. Good deal. Now, either you or somebody else measure how much is there. Now, every little mark is 2 because there's 100, 110, 20, 30, so 10, 20, 30, 40, 50. So there's 5 in between there. So every mark is 2. Say again? 82. So that is your volume of the salt. Now, this is measured in milliliters. What does yours say? Cubic centimeters. But guess what, team? A cubic centimeter is a milliliter. They're the same measure. So that'd be, what you say, 82?
82.
All right. Now, let's do the granite. Someone want to come up and release the granite into it? And guess what? We don't need to take the salt out because if the granite will fit, which it will, it's just going to displace a certain amount of water. So, blow it very slowly and gently into there. Okay. Before your fingers get wet, release it. Okay. All got below the water, right? Yep. Okay. Someone want to come up and do the pour? Oh, we need to dump this one out. Okay. Who wants to do the pour? Come on. Help me, somebody. Who hasn't done something? Oh, you've already done something. All right, you haven't done anything, lazy bones. Okay.
It's a long walk over there.
What's that?
It's a long walk over there.
Oh man,
I
I'm
gotta go on an
sweating.
adventure to get
Okay.
over here.
Wearing me out just watching it, okay? Take this water and pour it into there. Just cause this is, yeah. Got it all? Okay. Now you want to pour it into here. Use the spout, yeah. Oh, you're doing so well. For a beginner. Okay. All right. Now measure and see what the volume of the water was for here. Every little mark is 2 milliliters.
About 146.
146. Okay, 146 milliliters. Okay.
That was for.
That was granite, the volume of granite. Okay, now before I let go, I need to see if I can run my spillage here. This will.
Need help.
I think I got it. Trying not to spill much. Yeah, there we go. Okay. Success. Okay. Y'all see any paper towels in here? I think all well, just put that paper towel. All right, I'll get it later. Okay. Those with calculators, we're ready for the calculation part. Density. Anyone know how it's defined? Okay. Mass by the volume. You can tell by the units. Grams per cubic centimeter. So divide mass of basalt by the volume of basalt. Oh, before you do that, any guesses? Who's going to have the greatest density here? You have the numbers in front of you. What would you say?
Granite.
Okay, I hear granite. Okay, let's do the calculation. Mass of basalt divided by volume of basalt. Anyone got an answer yet?
1.98.
1.9? 98? Is that what you said?
Yeah.
Okay, and that's grams per cubic centimeter. Okay, is that what you got too?
Yes.
Okay. Okay. All right. Now the granite. Enter the mass, divide by the volume. What do you get?
3.08.
Okay, something is seriously wrong here. Did we get down the... I've already dumped it. No, I didn't. Okay.
Were we supposed to take the salt out?
What's that?
Were we supposed to take the
No, it doesn't matter. It was just the volume of water. I think I know what the problem became. There was a little bit of spillage here, and that probably is making the difference. I've never had it come up. It's certainly not this big a difference. Because in reality, guess what? The salt is denser than granite. And I don't know how the numbers came out. That's why maybe I should have taken a closer look. I'm wondering if we were reading the scales right and everything else. Is it worth doing it again? I think so, because that was somewhat suspicious. Okay? I'll try to take a closer look now. I was just letting y'all do the reading. Okay. And what I'm going to do... All right, let's start over again. Okay. This. A little bit more to this too. Jesus. Now be careful, folks, as you're moving here, because the floor has gotten a little wet. It's not as bad as that terrazzo outside, but it can be slick. Ooh. There was maybe part of an issue right there. I think we still have water. Oh no, I spilled that. Okay, that's okay. So we're gonna have a little bit more. Okay. Has anyone not done something? Few people, right? Brittany, I know. I call her. She's trying to act real busy. Okay. Let's try it again. Okay, first thing, well, let's first weigh or determine the masses of our two rocks. Two types of rock, anyway. Okay? Who wants to do it? I think two people are the only two that haven't done anything, right? Okay. All right. Okay, let's do the salt first and the dark one. Got it. All of those on there. Oh wait, did you zero the scale first? Make sure it was zeroed. May have been, I don't know. Yeah, any way you want to do it on there. Okay? $162. Okay. Where were you reading from? Okay. And you see 2 would be the second little mark right up there. Okay, 164. 164 grams. Okay? And let's go on and do the granite. By popular demand, okay?
I'll do something.
Okay. I can tell it's exciting for you. Okay, take those off and put the granite on. Yep. Do the mass of the granite. Mass of the granite. Take those off.
What is this called?
Huh? Oh, that our text scale, as you mentioned, food. What is it? 448. 448 grams was the gram. Okay? All right. Now you can do, anyone can do as much as little, everybody's done something as you want. Anyone come up and fill this thing with water. Anyone will do.
You want those?
I want to get it full to the brim. Let's see if you can do any more. Ah, there it is. No, I think you're right. It was full to the brim. Okay. Who's next? Want to very slowly put the salt in? Anyone can. Very anxious to volunteer. Okay. Yeah. Oh, no, don't put your fingers in. No, that's okay. Let's start that. Okay. We don't want fingers. We want only right. So before your fingers get wet, release. But wait, we've got to refill.
Take time.
And I'll get rid of it. Fill it too. Okay. Okay. We're gonna need a mop or two. Okay. Now, very slowly lower. Huh?
No, the bottom one.
Okay.
There you go.
Okay. Okay, but don't let your fingers get wet. Just before your finger gets wet, then release it. Okay, good. You don't want to do more? Okay.
Oh,
Yeah, do as many as you like. Keep things along. Ooh, okay. A little less flourish. Okay. Okay. Good. Okay. Who wants to do the measurement? Oh wait, we're going forward here first. Okay. Who wants to do the transfer? Anyone can. I don't care now. Come on. Somebody.
You done one?
Yeah, everybody. I'm holding it. Okay, thank
That
you.
was smart.
Okay. You want to take this and pour it into there? Yeah, you can. Come on. Take this water and pour it into the next size container. The only reason we do that is the second one has a spout. Get it all in? Okay. Now, take that and pour it into this graduated cylinder. Okay. Read the result. Take it. 51 cubic centimeters. Okay, what was it last time?
82. There's a lot more water in that than before.
Okay. I wonder if it was misread. 82 would have been up here. I don't think it was that much, was it? Was it?
It was 82. It was all the way up there when I read it.
Okay.
There might have been water.
Well, I don't know, there must have been some water in here then that we didn't account for or something, because that sounds more reasonable. Okay, let's try it, see what happens.
Is that 51,
Huh?
52?
51 or 52.
Yeah. All right. Okay. Okay, someone wants to put the salt in, the granite in. Somebody please, okay. Now. Okay, okay. Yeah. Oh, okay. I think, see, that happened before. I think some of the water went outside, and this is not getting totally wet.
Get it all in.
Yeah. We're gonna have to restart on this one, okay?
Again?
No, not all, just this one, okay?
So you, how you want to
Go fill this up, water for me.
recap?
Yeah, that's right. You gotta fill it first. Gotta be full. Oh, we had some there. That would have worked. I'm sorry. Yeah, pour some of that in. Yeah.
You go pour this out now?
No, wait. You might need it. You gotta get it all the way full. Okay. Now. Set it down and we'll pour this into
Or
there.
can I put water in?
Huh?
Oh, okay.
Yeah. This has to be empty. Okay. Now, what I would do if I were you is target the low area here. Don't put it on top of much of that. So, yeah, no, I would do the big end first. Yeah, you did it right first. Okay. Take it over here and put it in very slowly. You want all the water to make it into here. Okay. Keep lowering, and right before your fingers get wet. Okay. Okay, and it all got below water this time. That's good. Okay, you have to do this?
Yes.
Okay. Okay. Now pour this water into there. Get it all. Okay. Now pour that into here. All right. There's the water you got. That's 176. 176. What did we have last time?
146.
Okay. I think we had a fair amount of spillage before. That was where our problem was. Okay. Now do your calculation. We're going to have to take this down anyway, so here it goes. Let's get it over there.
Maybe it'll be a little great.
All right. What did we get that time?
The salt's 3.21.
Okay.
And granite is 2.55.
All right. Those are much closer to the numbers I'm used to seeing. We may have not gotten it quite right on basalt, maybe a little bit lower, but basalt is denser than granite. Okay? Huh?
That's,
Okay, did you?
448.
Yeah. Okay. Yeah. All right. That's it for the physical part of the lab. The rest of the lab is answering questions. Okay? For those who are wanting to make up tests, you can answer your questions at home and make up your test now if you want to. We've got plenty of time for both, I think. But yeah, it's almost 4 o'clock. Did I mark the roll again?
No.
No. Let me mark the roll before I forget it. No one has left since We started this mess, have we? I mean, this stuff, have we? Okay. There it is. Brendan is still here. Brianna is here. Darius is here. Emmanuel is here. Tyra is here. Coco didn't come back yet. Bianca never made it in. James didn't make it in. Josh is still here. Gary didn't make it in. Carl is still here. Tamisha's still here. Shelby's still here. Brittany's still here. And Terry still here. Okay. Finally got the roll call. Okay. So, up to you. Would you rather move back to 261, or are you happy to stay here? Huh? Okay. So I would suggest, if you have tests to make up, you can do that. Some of you asked me about that, so you can do that if you want to. The rest, I would say, work on your questions, because that's going to help you for your test. And when you finish all of those, or if you want to work on those at home, you can do that too. So it's up to you what you do next. Yes. Okay. Which one do you need of ones?
17.
Huh?
17.
17. That was the last one? Okay.
Hey, we're doing these questions, right?
Oh yeah. Oh yeah. Let's do that first. I'm sorry. Good for reminding me. Because some of you might have some questions on those. So since I'm here, and let me move my, well, I'll stay here. Okay. So let's take a look at the results. Okay. In what ways do igneous rocks have different properties? Think of some properties that say these two igneous rocks have. How are they different? Okay, certainly there's density. Okay? One's a darker color. Okay, so color is a different properties. Density, color. Say again?
Volume.
Okay, yeah, volume would be this piece of rock. You could have a big volume granite or small volume granite. So that's not a particular rock. What would you say?
Third form of hot molten mass of melted rock.
Okay, say that one.
Melted rock, they're formed by.
Okay. Okay. Now, both of these were formed by melting rock cooling, because these are both igneous rocks. Okay? But what tells you something about the difference in their cooling?
Intrusive.
The what?
Intrusive and extrusive.
Okay. One of these is probably intrusive, one extrusive. Which was which? Say again?
Granite's extrusive,
Why?
different color.
Now, color doesn't really have that much to do with the intrusive, extrusive. Second?
One's got crystals in it.
Both of them have crystals. But
The granite has crystals.
yes, well, the granite has larger crystal size. You can see those big old crystals. The basalt, yeah, it has crystals, but they're tiny. What does that tell you? Oh, wait, we'll get to that later. So crystal size, which is also coarseness. Okay, coarse or fine. Anyone think of any others? Definitely some different properties. Now, number 2, explain the theoretical process or processes responsible for producing the different properties in igneous rock. You mentioned color first. What are some of the things that contribute to different color between the granite and the basalt, or any two rocks?
Iron.
Okay, the iron content generally makes the rock darker. Okay, so the content of the materials. The more silica in there, the lighter the color. Other pieces of granite that I didn't bring forth, they were too big for our scale, they're very light colored. So the constituent material that contributes to color. What was the second property you mentioned? Density? Okay, what contributes to density? Iron content again, the constituent materials, exactly. So that contributes both to color and to density, okay? And the iron content will be darker color and heavier density. Okay, what's your next one? Did you have another one? The core size, okay? What contributes to that? Not the material content, okay? What contributes to the the coarseness or fineness or crystal size? Okay, close but not quite.
The amount of friction?
No, you're close to it when you said that. What do you mean by amount of heat?
How fast it cools.
Exactly, the rate of cooling. The rate of cooling is the theoretical process that's responsible for producing different crystal sizes. Which would have cooled faster, which slower?
The granite would cool faster.
No, the granite cools slower because of larger crystal size. The finer grain, small crystal size basalt meant it cooled really quickly. It probably cooled at the bottom of the ocean. That would have been pretty quick, you know, the volcanic material coming up and cooling really fast. Okay, number 3. According to the experimental evidence of this investigation, propose an explanation for the observation that the bulk of the Earth's continents are granite and basalt is found mostly in the Earth's interior. I'm going to clarify that a little beneath the ocean. That's what we mean interior here. It's not really good wording there. So according to this experimental evidence of this investigation, propose an explanation for the observation that the bulk of the Earth's continents are granite and that basalt is found mostly in the Earth's interior.
Most of the rock under the ocean cools faster than time.
Okay, that's I think that nails it right there. The rocks, volcanic rock, lava, magma coming up underwater is going to cool pretty quickly. Okay, whereas the granite, now it was intrusive because it's large crystal size. It cooled slowly, but it cooled underneath the surface of the Earth. Now the other thing is the volcanic rock could have more iron in it. The last, if you remember the Bowen reaction series, remember those cooling, the ones that cooled fastest were the high iron way down below. Then you're left with the more siliceous silica material more at the surface, but still underneath. So your lighter color, lower iron content cooled last, which would be near the surface. Okay, so that's also part of it. And then number 4, you just have to answer. Okay, there is no correct or incorrect answer, but if there's no answer, you don't get any points for that one. Okay. Okay, if you have any questions, I'll be glad to try to answer them. Yes? Okay. Yeah, that's a good thing. And the other thing is that the volcanic material will contain more iron or it comes from deeper. Okay. The granite, even though it's still intrusive rock, it's the last on the Bowen, what do they call that? Reaction series, I think it is. And that was in the light material. And that was big hot. Anything that will be better. He'll have to tell you whether he thought before or what he thought before. I can't answer that for him. Thanks, Brianna, for bringing him.
Mr. Fowler,
Yes.
what about this invitation to inquiry?
Okay, you can read and do with that if you want to, but that's not part of the lab.
Okay.
There are a couple of those that we will do in lab. I don't think any in this class, but in one of my other classes we do something with that.
Yeah, you gotta do your questions without. I'm gonna do this weekend or something. So I can't get Tuesday.
Bless you.
See what I meant by wet lab?
So, are we done?
Before you turn in your labs, and you got a week to do that, but be sure you do your questions, right?
Okay, we can do those at home, right?
You can do them at home if you like. If you are still owe me a test, this would be a great time to get the test done. And I would highly recommend do the questions before you take the test on Thursday. But that's up to you. Yes. Okay, 14. Okay. Okay. All right. You finished the questions too? Oh, that's the other deck. Okay, great. Okay.
What is Thursday?
I think it may be at the end of that thing. That's where it used to be. I don't know if it still is or not. Is it right there? No. In the hall? Is it out there? Okay. Okay, anyone else need to do chapter 14 test? All right, you needed 17? Okay. I think we test 4, right? Remember, for the test, you can't have formula and equation sheet if you got it. Finish your questions too? Huh? The questions? There's 15 questions? Yeah. Okay. I was telling you, this only adds up to 10 points. 10 points. It's a 25-point lab. The other 15 points come from the questions in the book. There's 16, what do they call them? Questions for thought and 4 for further inquiry or something like that. So out of those 20 questions, do any 15 or more.
Gotcha.
And you can write them on another piece of paper. You probably will need more room than that. You can write some of them there if you wish. And those are the ones I suggest that you get done before the test. You don't have to, that's up to you. It certainly seems like that would be helpful. And this is a lab, so y'all can work together on questions, you know. This is a lab. There's nothing wrong with that. Okay, are there any more questions, or should I go on and shut down so this can be uploaded? No more questions? Okay. If you have them, I'll just not have recorded answers, but they'll be answers. Okay, I hit the wrong thing.